Bismillahirrahmanirrahim. Assalamu alaikum students, I hope you are fine. My name is Iftikhar Babar and I am your physics teacher. Today is the first lecture of class 10th. We are going to start unit number 10. This is the first unit of class 10th. Simple harmonic motion and waves. In this chapter we will study about simple harmonic motion, damped oscillations, wave motion, types of waves and ripple tank. Our first topic is simple harmonic motion. Simple harmonic motion is a kind of vibratory motion. In your previous class, 9th class, you have studied about vibratory motion. Vibratory motion is a type of motion, to and fro motion of a body about its mean position is known as vibratory motion. For example, simple pendulum motion of swing. In simple pendulum, there are two positions in which the body moves. One is mean and other is extreme. Body move from mean to extreme and then another extreme position. So simple harmonic motion is also a kind of vibratory motion. Simple harmonic motion occurs when the net force is directly proportional to displacement from the mean position and always directed towards the mean position. According to this definition, if we increase the net force in the body, the displacement of the body will also be increased. And if we decrease the net force in the body, the displacement of the body will also be decreased. But it always directed towards mean position. Another definition of simple harmonic motion is the motion in which acceleration of the body is directly proportional to the displacement from the mean position and is always directed towards mean position. In this definition, acceleration is directly proportional to displacement because acceleration and net force both are directly proportional to each other. So we can say that acceleration is also directly proportional to displacement. We can prove it with the help of an example, motion of mass attached to a spring. Here we have a body which is having mass m and a spring. The one end of the spring is attached to the body and other end is attached with a firm support. In figure A, the body is at rest, there is no force acting on a body. So the body is in equilibrium. And this is a mean position of the body, where the body is at rest. Now if we apply the force on a body and move it towards right, this is a extreme position of the body, that is A. The length of the spring will also be increased. And now if we release the body will move from position A to position O due to restoring force. Students, restoring force is a force that pushes or pulls the object towards its mean position. And restoring force is a force which is stored in the body when we move it from point O to A. is a restoring force, and the body move from extreme position to mean position due to restoring force. At point O, the body will not stop here. Due to inertia, it will move from point O to B. B is another extreme position of the body. And then body will move from point B to O and then A. And then it will complete its one vibration. We can prove it mathematically. According to Hooke's law, the force is applied on the spring is directly proportional to change in length x of the spring. In 9th class, we have studied about Hooke's law. Stress is directly proportional to strain. Here, stress is a force and strain is a change in length x of the spring. So we will write here F is directly proportional to minus x. Here F is the force and x is the displacement from mean to extreme position. Displacement of the body from mean to extreme position. Okay. Here negative sign shows that restoring force of a spring is opposite to the direction of the motion or displacement of the body from the mean position. Negative sign shows that restoring force of spring is opposite to the direction of motion. We apply the force on a body towards right, but the body will move towards left. F is equal to minus kx. K is a proportionality constant. It is called spring constant. K is equal minus F over x. This is a formula of spring constant. According to this formula, if we increase the force, then the value of K will also be increased. But it depends upon the nature of the spring. If the spring is stiff or hard, the value of K will be large. If the spring is soft, then the value of K will be small. So the value of K depends upon the nature of the spring. Here we have the definition of spring constant. K, the ratio of force acting on spring to increase its length. The unit of spring constant is Newton per meter, because the unit of force is Newton and the unit of displacement is meter. So it becomes Newton per meter. Newton m-1. According to second law of motion, F is equal to ma. By comparing question 1 and 2, ma is equal minus kx, a is equal minus k over mx, a is equal minus constant x, because k over m term is constant. Here k is constant and m is also constant. So we can write here a is directly proportional to minus x. definition of simple harmonic motion. This shows that acceleration is directly proportional to displacement from mean position. Hence, the horizontal motion of a mass spring system is an example of simple harmonic motion. Definition of restoring force is: a restoring force always pushes or pulls the object performing oscillatory motion towards mean position. Now we will discuss speed and acceleration of the body between positions A and B. At position O, the body is at rest. There is no force acting on the body. When the body moves from O to A, by applying the force and then release it, the body starts moving from A to O mean position under the action of restoring force. When the body is about to reach at O, its speed is maximum. Due to inertia, the body does not stop at point O and continue its motion towards point B and reach at point B. Its velocity, its speed reduces to 0. So we can say that speed at point O at mean position is maximum and speed at point A and B at extreme position is 0. Now we discuss acceleration of body between positions A and B. Acceleration of the body is directly proportional to its displacement from the mean position and is always directed towards the mean position. As a mass M moves towards the point O, its displacement x goes on decreasing and velocity goes on increasing. So acceleration of the body also decreases. On reaching the point O, x becomes 0 and so the acceleration of the mass also reduces to 0. The acceleration of mass remains towards mean position when it moves from point O to B, because the speed of the mass starts decreasing as it passes the point O. The body, after coming to rest at point B, again returns to the point O under the action of restoring force. And this process continues and the body keeps on vibrating between points A and B. So acceleration of point O is 0. Acceleration at point A and B is maximum. Similarly, kinetic energy of the body at point O is 0 and potential energy is maximum. Kinetic energy of the body at point A is 0 and potential energy is maximum because this is a energy stored in the body. And at point O, kinetic energy is maximum and potential energy is equal to 0. Similarly, kinetic energy at point P is 0 and potential energy is maximum. We can also find the time period of the body. Definition of time period is the time taken by the vibrating body to complete its one vibration. The mass attached to a spring completes its one vibration when it moves from O to A, then A to B, and then come back to point O. We can find the time period of mass attached to a spring with the help of this formula. T is equal to 2 pi under root m over k. Here m is a mass of the body and k is a spring constant. Okay students, this is the first lecture of class 10th. You have to learn this topic. This is a very important topic. Allah Hafiz.